Hello everyone. My name is Harsha Kokel and I'm presenting our work on reducing action labels in planning domains. This work is done in collaboration with Junkyu, Michael Katz, Kavitha, Srinivas, and Shirin Sohrabi at IBM Research. So, planning tasks represent label transition systems, LTS. In LTS, each state is represented as node, and transition between states are represented by labeled edges. However, each transition is not uniquely identified. That is, a unique label is not provided for each transition. Rather, to reduce the number of labels, LTS uses a unique label for each ground action. So the transitions induced by the same action on a different states have the same label. For example, the transition between the state PQR and QRS and the transition between PT and ST both have the same label A, indicating the ground action A. These labels are primarily used to distinguish applicable actions in a given state. So, no two outgoing edges from the same state can have the same label. In our work, we seek to identify a smaller, sufficient set of labels that might attain this property of having distinguishable actions. That is, it might still satisfy the constraint that no two outgoing edges should have the same label. By doing so, we aim to reduce the label set in LTS. The main intuition that we use is that of a mutually exclusive precondition. So consider these two actions for action D and action E that are mentioned here. If the precondition of E is changed to not P and D, and the precondition of D is P and D, then it is clear that action E and D cannot be applied in the same state ever. Hence, using the same label for the transition PT to TU and from ST to VW would still satisfy, would still produce an LTS that can distinguish two applicable actions or two outgoing edges. So we use this intuition and formalize our approach in the remaining slides. But before I dive into the formalism, let me also give a brief motivation from the perspective of reinforcement learning. So, the reduction in label is especially useful in reinforcement learning frameworks or model free approaches where transition dynamics are decoupled from the action labels. So, for example, in the MDP, we have separate A, that is the action labels or the action space, and the transition dynamics T, also called transition function. So most RL approaches cannot handle a large number of discrete actions, but they can handle complex transition functions. Uh, to give an estimate, most RL benchmark usually have less than 100 actions. For example, the Atari benchmark have at most 18 actions. Hence, reducing the number of action labels in LTS can also enable the use of state-of-the-art RL approaches for planning. So the contribution of this work are as follows. First, we characterize a valid label reduction for classical planning task. Then we propose a way to automatically obtain such a reduction and demonstrate that our approach achieves a significant reduction. And finally, we demonstrate two use cases of our approach. One in learning a model-free RL agent for planning tasks, and second, for querying applicable actions for a given state in lifted successor generator. So we define a valid label reduction function first. A label reduction function is valid if any two distinct ground action labels that are applicable in the same reachable state are assigned distinct labels. It is equivalent to saying that two outgoing edges cannot have the same label. So any label reduction that maintains that property is a valid label reduction. Next, I introduce our proposed approach of automatically obtaining the label reduction function. But before we do that, let us see what causes large number of labels or grounded actions in planning tasks. Consider the gripper domain here, where a robot moves between two rooms. The PDDL task in this domain can be represented like this. Let us zoom in on the pick operator. The number of grounded actions generated by this operator is the number of balls times number of rooms times number of grippers. By assigning unique label to each grounded action, the number of labels generated is actually a factor of number of parameters and the number of objects. But let us consider the second parameter, room, here. All applicable groundings of the operator pick in any given state will have the same value for the variable r, that is the current room the robot is in. Therefore, this parameter is not essential for distinguishing applicable actions in the LTS system. So if we remove that parameter from the action label, we can obtain a reduced label set, which can still distinguish between all the applicable actions in the same state. So such a label reduction function is valid. So we can do that because we know that at Robbie room 1 and at Robbie room 2, which are part of the precondition of the pick operator, are mutually exclusive. So the precondition at Robbie R ensures that pick ball 1 room 1 G1 and pick ball 1 room 2 G1 cannot be applied in the same state. So these actions are mutually exclusive. We can split all the grounded actions into groups of mutually exclusive actions, and we call such groups as applicable action mutex group. A label reduction function that assigns same label to all these actions, all the actions in the AAMG, is a valid label reduction. Notice that such a group can essentially be represented using just pick ball gripper. So pick question mark B question mark G. It is equivalent to removing the parameter R from the lifted action model. So some parameters of the lifted action models do not distinguish the applicable actions while others do. So we call the later, the parameters that distinguish the applicable actions as seed parameters. In this case, ball and gripper are the seed parameters. The room is not. So we formulate the problem of identifying valid label reduction as the problem of identifying seed parameters. The solution to the seed parameters will also provide solution to the label reduction problem. So the key question is how to identify the parameter seeds. To do that, we first find relevant lifted mutex group. We define two conditions for a lifted mutex group to be relevant to a schematic operator. Once we have the relevant lifted mutex group, we define a delete tree planning problem. The problem contains a predicate marked and an object for each parameter in the schematic operator. We define two types of action, seed X for each parameter X and get L for each relevant lifted mutex group L. The solution to this delete planning problem is a plan containing a sequence of seed and mark actions. For every seed action in the plan, the respective parameter is a parameter seed. I invite everyone to look at the problem definition and the details in the paper. So far, here we characterized a valid label reduction and introduced an approach to find valid label reduction by identifying seed parameters. To do that, we notice that we used lifted mutex groups. Next, we demonstrate the significance of our approach. So figure A on the left presents the reduction on each PDDL problem instance for 14 IPC domains. And figure on the right demonstrates the reduction on each PDDL problem instance for 7 hard-to-ground domains. Notice that both these axes are log scales. So any point below the diagonal indicates that the reduced label set generated is smaller than the original one. The distance from the diagonal indicates the significance of the reduction. The gray dashed line below the diagonals represent the order of the magnitude. So our experiments show significant reduction of label set in most problem instances, going up to 2 order of magnitude for the IPC domains and up to 10 order of magnitudes on hard to ground domains. Next, I demonstrate two use cases of our approach. The first use case is in reinforcement learning agents. The figure represents a significant advantage in sample efficiency obtained by using reduced action labels uh, while learning RL agents. The green line represents the learning curve of RL agents that use reduced action space. We compare that with the red line, that is the learning curve of RL agents with default action space, that is, using a unique label for each grounded action. We present results on 4 domains, ferry, gripper, blocks, and logistics here. Notice that the transition function are exactly the same in both these cases, except now we have a reduced label set. In lifted successor generator, the task of querying applicable actions is posed as a database query. The complexity of executing that query is a function of a table size. With our approach of identifying parameter seeds, we can reduce the table size significantly and hence improve the query complexity. For our experiments, we use power lifted, a recently introduced lifted successor generator, and we compare the table sizes in power lifted with and without the parameter seeds just before the query is performed. So the values on the x-axis represent the table sizes in power lifted, and value on the y-axis represent table sizes in um, power lifted with parameter seeds. As you see, by identifying parameter seeds, we are able to reduce table sizes in significant number of problem instances. More details on how we use parameter seeds to reduce table sizes is available in the paper. We also have the proof of how the solution to the parameter seed set problem provides a valid label reduction. I invite everyone to look at the paper. I can take any questions at this time.